And tell me all the dates for which the recording is not sent. I'll send it.
Okay, sure. Sir, I think only 9th May and 12th May are missing, sir.
Okay. So, okay, there are two things. Like we can either study capacitor after the current, or we can study capacitor. So the problem is, if I will teach the capacitor first, then I will teach the concept of current and electricity here only. Or if I teach it later on, then we can use the concept of current and electricity in capacitor. So I think what will be better is like we should start with the current first. We will finish the current and electricity. We'll come back to chapter of capacitor and then we'll finish it.
Okay, sir. So you were telling me about doing gravitation, sir.
Yeah, right. So we can finish gravitation also, no? Yeah. So I think let's finish the gravitation. That's better.
Okay, sir. Sir, can you just do like a revision of electrostatics for this one? I mean, like
not much. Like you will be able to derive it. It's not very difficult.
okay, sir.
So in gravitation, of course, the first thing we talk about is called mass, and the mass can have variety of definitions. So the mass can be gravitational, the mass can be inertial, mass can be relativistic. So we have many categories of mass. So we have gravitational mass. We have inertial mass. We have relativistic mass. And then we have Bose-Einstein condensate. And maybe there are many more, I don't know. So the gravitational mass and inertial mass, we call it mass. And actually, earlier it was thought that these are different, but eventually Einstein proved that no, these are same thing. You need not to call it by a different name. So what is the inertial mass? So in a short, I can tell you, like when you use the formula F equals to ma, the Newton's laws of motion, the mass which comes as a part of this relation, we call inertia. And gravitational mass is what? So definitely this we are going to learn now. So the mass which appears in the formula of Newton's law of gravitation, so we call it gravitational mass. Okay.
Yes.
So these are the masses, and of course the relativistic mass you have already seen. It is a rest mass upon 1 minus, and in fact this is also the rest mass. So in physics, mass is a variant. So the striking difference from the electrostatics and charge and gravitation and mass is that mass is not a invariant, mass is a variant. Mass is variant, which means the value of mass will change from frame to frame. And Einstein saw mass as a embodiment of energy, not just as mass. So in the formula of E equals to mc square, the m is not just mass. M is the total energy of a mass. Like by using m, we try to make sure that the total energy of the body can be explained, which also takes care of the kinetic energy. And if you use the Einstein relation, and therefore you can clearly see that the momentum we also write in relativistic as mv, and the m itself is m not v by. Understood?
Yes.
So the value of E square will be m naught c square upon 1 minus v square by c square, and the value of p square itself is m naught square by this upon 1 minus v square by c square, and therefore the value of p square and c square, if you want to write, so why we are doing this? I mean, of course, we're trying to replace. We're trying to add the value of p square and this. Sorry, we're trying to add this value, this value. So, or we can just replace these equations. So the p square we got is okay. Let's write p square. P square is how much? M square v square upon 1 minus v square by c square, right? So let me write down. So 1 minus v square by c square is and therefore I can write here as 1 by v square minus 1 by c square is m naught by p whole square, right? We can write like this, something like this.
Yes.
So 1 by v square is so c square by v square. If you multiply by c square, it becomes 1 plus m naught c whole square by p square. Like this, we can write. And so c square minus by v square. Okay, we can keep this ratio intact. So we can write as oh, like this is okay. This is fine. We can derive now. That's almost close. And the energy square we got as answer is m naught c square power whole square, right? Upon 1 minus v square by c square, right?
Yes.
So E square into 1 minus v square by c square is m naught c square whole power, like 2. So if we substitute the value of 1 upon, we can attach 1 plus so it becomes 1 minus p square by p square plus like this. Okay. I'm just deriving a dreadly formula. So E square, you can take LCM. So it will become this only, no? Right?
Yes.
This cancels out and this cancels out. So if I multiply both sides, what you get is c square into p square plus e square is how much? P square c square plus. So this formula I started with in electrostatics, the energy relation maybe. So the energy and momentum are related with the rest mass by this formula. You can see the formula. And what is interesting here is to note that even those entity, those physical quantities which do not have rest mass can have momentum. So let's say for photons, for photon, there is no rest mass. And because the photon cannot have the rest mass, still you can see the formula will be E square is P square C square. And therefore you can attach E equals to P into C, which means momentum is not just property of massive particle, momentum is also property of electromagnetic wave also. When I say photon, it means EM wave. So momentum is something which is carried by the non-massive particle. And this formula is again very, very interesting because, and this will help you in chemistry in realizing that momentum is not always associated with mass of the body. So the momentum we can attach E by C. For EM waves, we know that energy we write as h nu called the Planck's law or sc by lambda. And definition of momentum says it is E by C, which will give you h by lambda. So now we know why we call momentum as h by lambda.
Yes, sir.
And also, if we have a matter that is something which is having mass, and if you know the momentum, then the wavelength associated with the matter called the de Broglie wavelength or de Broglie wavelength. So lambda de Broglie is h by p. Anything with momentum will have the lambda d. Now the problem is the wave character of matter is not perceptible by any technological advancement. The reason is h itself is very small, right?
Yes, sir.
And in the real life, even if you take a particle of few grams, it will not make the lambda very small. And you can imagine this lambda, let's say if I take p equals to 1 kg meter per second, the lambda of this value, which is of order, so the order of lambda is 10 to the power minus 4 meter. Is it possible to detect such a small wave?
No, sir.
The answer is no. So the wavelength associated with our matter in our day-to-day life interaction is so small that it cannot be detected or the property cannot be felt. Whereas, if we talk about the particles like electron, so the electron having mass itself, how much?
9.1 into 10 power minus 31 kg.
So let's say if it is moving with the velocity of the electron, the normal velocity we take as 10 power 6 meter per second, which is 1/100th of light. Still, you can see that the momentum of electron will be me into v, which is quite significant actually, isn't it? So m into v will be 9.1 10 power minus 25. correct?
Yes.
kg meter per second. And therefore, the lambda de Broglie of electron, if we try to calculate, the order is quite good actually. It's like a nanometer order. And our visible light is also in that range, right? So we
Yes.
can say that this kind of wavelength is perceptible, or you can say detectable. And therefore, the wave-like property has been shown by these particles. And when I say the wave-like property, later on you will come to know something like superposition of wave, like it creates interference or diffraction. So these phenomena, which is expected from the wave, has been found to be also occurring with these particles, which are very light in weight. And therefore, that was the kind of confirmation to the fact that it is not that the wave can have momentum. Even a particle with momentum can have a wave-like properties, like it can diffract and it can show the various other superposition phenomena. So lighter particles exhibit, and in our day-to-day life, because we are very heavy, our associated wavelength is so small that it cannot be perceived. So what does it mean when I say you can perceive? Perceive means if you can see a person, you can see the person as a whole. You don't see a blur image, isn't it?
Yes.
But if you look at the wings of the fan, you don't see the wings clearly because it's quite blurred. Understood? So you
Yes.
can entail the blurriness to some sort of, you can say, the wave-like character, because wave is something like delocalized. You don't see at one location. So the wings are like although we have only just 3 blades, but it looks like it is spanning the entire disk. It is
Yes.
spanning the entire circle, and the whole circle is our blades. The reason is it is moving so fast that in our perceptible world, we see the wings not at one place but every place. Understand?
Yes.
Okay. Anyway, so why I was talking this? Because I wanted to derive this formula, and
Sir, I don't exactly understand how P is equal to H by lambda, that part came, sir.
energy E by C the momentum, no? This formula.
Yes, sir.
If mass is 0, then we write energy is
Oh,
momentum
yes, sir.
times speed of light. So momentum is energy upon C.
Yes, sir.
And Planck said E equals to h nu, and nu is C by lambda, right?
Yes, sir.
So E by C will be how much from here?
H by lambda.
But E by C is equal
Momentum.
momentum. So momentum is h by lambda, right?
Okay, sir. Yes, sir.
Okay, so this is part of your chemistry also. In physics also we study. It's not a big deal. But mostly these things are covered in the chemistry classes, so we don't cover. So I just wanted to give you the more deeper insight that how this formula came into picture. Okay.
Okay, sir.
Okay. Now these are things which are not required. What we need to know is only the concept of mass, and the mass actually refers to the most fundamental characteristic of a matter, and by virtue of this characteristic, they create a field around themselves which extends up to infinity, and this field we call gravitational field. Okay, so we call this as gravitational field. And this gravitational field will let other mass to interact. It means if you bring some other mass called, let's call a test mass, then the pre-existing gravitational field will apply force of attraction on the test mass. So you can say that mass is the fundamental characteristic of a matter by virtue of which it can create a field which in turn can interact with any other mass. Okay. So let's put a small definition of mass. It is the one of the most fundamental characteristic of any matter by virtue of which it creates a field around itself called gravitational field, which in turn can apply force, so which in turn can apply force on any other mass. So that is the whole purpose of mass. You create a field and field does the interaction part. Mass never interacts, field interacts. That's simple. But in a common literature, when I say mass is interacting, we refer to the same concept, but it is very much implicit in literature, which is somewhat misleading for many readers. So what I will say is mass interact because the masses interact with each other through their field. Okay. So if we have two mass, then the field of every mass will be present everywhere, but we can get one point at which the field of the two can cancel out. So this point will be the point at which no field will exist, and this point we can say the neutral point or the point of equilibrium. So if you bring any mass in this location particularly, then mass will not move, right?
Yes.
Because mass only interact with the localized field, just like charge we discussed. So the point where the field is absent, things will, I mean, the force will not come, the gravitational force will not come into picture. And why these concepts are important? I mean, if I just talk about the simple launching of, let's say this is Earth, this is Moon, and you want to launch a satellite from the Earth to Moon. Now, the beauty of this concept is that the fuel consumption is only up to this point, because the moment you cross this point, the gravity of moon will become dominant, and so the rest part of the journey will be under the gravitational attraction of moon. You need not to worry. You just let yourself free. You will eventually land on the moon without any doubt. So that's the beauty of this. Uh, and then later on, you will study about the aiming parameter. Aiming parameter is all about like how close you can reach the planet. So generally, the landing process is done in a like a very phased manner, because if a satellite will hit like this, it's difficult to stop. So it will make a bump with extreme momentum, and it will be like the biggest exposure. Rather, it goes this way. So they project the satellite in such a way that it doesn't. So of course, the moon is attracting. So I throw something like this, and moon is pulling this way. So it will just turn like this. So this prevents the sudden drop, and then you make some round around the moon. You slow down your speed, and you slowly land on the surface. Landing is done in a very different fashion. You make a round around the planet to land actually. Understood?
Yes, sir.
So these concepts are important. Like of course, when we will learn about the satellites and planets, we'll solve this question also. We'll do it. In fact, we'll solve these questions. So coming back to the chapter, so we'll not go much deeper into derivation because we have done this in electrostatics. I'll just mention a few points. Let's say Newton's law of gravitation. So Newton's law of gravitation is what? If we have two point-like masses kept at a separation, R, then Newton said that the force of attraction is proportional to product of masses and inversely proportional to square of the separation. So force of attraction is proportional to product of masses, and therefore it is equal to some constant which we put as G. And the only thing is that the attraction force is always gravitational, so it is like the direction is opposite to the case of repulsion. So if you want to write in vector form, okay, now the value of G should be known to you. What is the value of G? So the G is called universal gravitational constant, and it is equals to 6.67 into 10 to the power minus 11 Newton meter square per kg square. And you can see G is very small, right? G is very small.
Yes.
So if I give you two mass of 1 kg each kept at a separation of 1 meter, the force will be equal to this value. And therefore, the lighter objects cannot attract anywhere significant, because 10 to the power minus 11 Newton is something which we don't feel at all. Understood?
Yes.
Or even though we feel, we don't perceive it compared to the other force. So that is why the force between human beings, between them is quite insignificant compared to the force between you and the earth. So essentially, we ignore the interaction of lighter masses, and we are predominantly governed by the gravitational force of earth, because that is the predominant feature among all other interactions. So The value of G was determined experimentally using the Cavendish experiment. So value of G was determined experimentally by Henry Cavendish. I think that's the name. So the setup was very simple. So there was a suspension point, and there is a metallic wire. And with the help of metallic wire, a massless rod was attached at the bottom. And 1 kg of gold ball. You can imagine that how expensive it is. You are attaching gold of 1 kg. That's expensive, right?
Yes.
But nevertheless, they never went to any jeweler to buy it. It was in their lab. So,
So why gold?
yeah, gold is like a heavy element, you can see, and it is corrosion free. So, in lab, we create something which can exist for like long time, right?
Yes,
So,
sir.
during the over the years, it should not corrode and lose mass. So technically, we use the more, you can say, novel element like gold. Platinum was not there that time, so that's why it was not used. And this experiment was performed in the era of Newton. So you can imagine how old this gold thing is. So I think
Yes.
gold was a logical choice. I won't say it's something really bad. I mean, yeah, it's logical. Okay, so
Oh,
apart from this gold, so what they did next was they brought some a similar gold and they kept at a distance like this. So now the wire is so thin that the force of attraction between just a moment. So this force will create a torque, right? If I call this force as F, then it will be like a couple force on the system. So
yes.
if I call the length as L, then torque about the axis will be how much? If I call this as axis, this is Z axis. Can you say this is 2FL?
Yes.
So what next? I mean, is this sufficient? No. So after that, you need to put a mirror. See the entire process. That's interesting. And from a distance, you draw a flash torch. Generally, I mean the flash torch is it hits the mirror at right angle. I mean at 90 degrees, so it will not deflect. It will come back, right? That's the whole idea.
Yes.
So it will retrace the path. So light will go this way and come this way. But what happens, like if if you bring this gold, if the I mean if there is a slightest tilt in the a twist in the rod, so twist in the suspended wire will do the shifting of the mirror.
Yes.
So if mirror will turn by a small angle, the light will deflect in other direction, isn't it?
Yes.
So to understand this, if this is a mirror, if a light is hitting this way at right angle, it will come and will bounce back. If the mirror will tilt a bit, even a small value, so now once you tilt like this, the normal will shift here. So this is the angle of incidence now. So light will come from the same direction, but this will not deflect the light in other direction, isn't it? Like this.
Yes.
Now the spot, like we put some wall at a distance, so you can see the spot of the light shifting from the initial spot position, because the twist is so small that we need to keep the wall very, very far away, so that think this way. If the mirror will tilt like this, if the light will turn this way, so to see make this significant, I have to increase L, correct?
Yes.
Or let's say this is R. So if R is very large, then the spot will shift from here to here, which is called R theta. So if theta is really small, I need to make R large enough to detect the turn. Okay.
Yes.
And you will come to know that if you turn by theta, this will be theta, this will be. So light turns by twice of the angle by which the mirror turns. Okay.
Yes.
So if theta is twist in suspended wire, then light will turn by 2 theta. Okay. So the deflection will be now twice than the before. And you will study in the chapter of SHM that the torque called the torsional torque, which is developed in the twisting rod or wire, is proportional to theta, and C is called torsional constant. So at equilibrium, the 2FL, which is the torque of the force, must be balanced by C theta, right?
Yes.
So wire will oppose the turning first further. So 2FL is equals to C theta, and that was the whole idea. So we got F C theta by 2. And
Yes.
all right. So if I take the masses equals to Gm square, and if this separation, which I haven't shown, is R, at equilibrium you can say R. So this is R square. So G we can write as C theta R square by. So this is how by simple experiment he was able to determine this G. And sometimes knowing the historical perspective even helps in solving some of the challenging problems of physics. Okay. So this was the Henry Cavendish and his experiment for the determination of universal gravitational constant. So the G is called, I hope you know, +9,
Yes.
universal gravitational constant. Okay. Okay. So now we can move further, like what really we need to do. So we'll talk about the variation of G, or let's talk about the gravitational field intensity. So it is similar to the electric field intensity, and we can represent by G vector. Now this, no, don't get confused this G with the acceleration due to gravity is symbolic G, because we can use the same symbol. But definition wise, it is again the same. It is the gravitational force per unit test mass. That's simple. It means if we have two mass, and if I want to know what is the gravitational intensity at the point P, so we bring a test mass. You may call this as source mass. So the G developed by the source mass will be okay, in vector form, you want to write minus Gm by R cube into R. Why minus n? Because it is going to be a volume. So basically, the force vector, how we write? Minus. So the way of writing will be, I need to again do the nomenclature. So if I have two masses M1, M2, so the force on one due to two will be like this, and force on two due to one will be like this, correct? And this direction is R21, the position vector of 2 with respect to 1, and this direction is R12, right?
Yes.
So what you can see that F12 and R21 are same. So we can say F12 is parallel to R21, correct?
Yes.
So F12, if two vectors are parallel, it means their unit vector will be same.
Yes.
So we can write as and the value of force will be how much? The magnitude is G M1 M2 by mod of, you can say, R21 whole square, because that's mod only at the end of the day.
Yes.
So we can take mod as R, so this will look better like minus, sorry, not mod, G M1 M2 by R cube into R21. But we want to make it in terms of 1-2 relation. So you can write F12 as minus G M1 M2 upon R cube into R1. Like I can just switch the order so that it can look nice. So 1-2, 1-2, 1-2 everywhere, right? So force on, you can say force on M due to capital M will be, okay. So the force on M will be towards this, correct?
Yes.
And the R is the, okay, so you can see R is the position vector of small m with respect to, so you can think like a 1 and 2. You can think like 1 and 2. So can you see clearly that so force on 2 due to 1 is how much? So we can say F into R21 by R21 mod, correct?
Yes, sir.
F is GM M by R square. R21 is what? It is R.
Yes, sir.
And direction wise they're opposite, no?
Yes,
This
sir.
is okay, that's it. So we can write as R. So that's why this form I wrote. So F21 in this case will be how much? Minus G capital M small m by R cube into R vector. So that's why the G at the point P we can define as F21 divided by M. And so the answer will be. So if you just want to write the magnitude, that's simple. You just write GM by R square. That's
Yes, sir.
nothing big deal. I mean, it's similar to the electrostatics.
Yes, sir.
So G, the modulus will be GM by R square. So this G is not the gravitational acceleration symbolically, but actually what we need to realize that acceleration by definition is same as F by M,
Yes, sir.
which is similar to the definition of G. And therefore, in gravitation, acceleration and G both represent same or both mean same. So acceleration due to gravity is actually, or you can say coincidentally, is gravitational field intensity as well. Understood?
Yes, sir. Sir, so I don't exactly understand the difference between the two, sir.
No, there's no difference actually. That's why I'm saying the way we define acceleration is also force upon mass, and the way
Yes,
we
sir.
define intensity is also force upon mass. So intensity is what is the intensity? Force per unit mass. And here we are saying force upon mass. That's interesting. Huh?
Yes, sir.
Like if you try to understand the the acceleration we define, try to say that how much force can generate how much acceleration. Let's say so that is the concept of inertial mass. So if I write F equals to m into A, so if you apply a force of 1 Newton on a mass of 1 kg, you get acceleration of 1 meter per second square.
Yes, sir.
Or the other way of saying is m is inertial mass is the force required to create an acceleration of 1 meter per second square. Then the mass of the object is called 1 kilogram. I mean, like you're just trying to touch your nose from two different directions.
Yes, sir.
So we're trying to define one in terms of other and vice versa. That's why there is a big debate called the hen and the egg. You know, the story of hen and egg, which came first. Okay. So Newton made the entire world confused that to define inertial mass, you need to define force, but to define force, you need to define the inertial mass before.
Yes, sir.
That's why these are called empirical relations. These are not the absolute relations. These are just empirical. So that we can do the
Okay, they
analysis.
reflect each other,
Pardon?
sort of. So
Pardon?
that means like the relations are made on how one affects the other.
Correct, correct, correct.
Okay,
So
sir.
these relations are not absolute. Like no one knows what exactly is the relation, but these relations are good enough to model the real world. So we have been able to model the real world by these simple relations. It is
Yes, sir.
said that the most complex things are most elegant and most simple. Things which appears really simple is the most elegant thing. So F equals to ma is so simple that, but it governs the entire universe. Imagine.
Yes, sir.
Yeah.
Sir, and here, like, are we making any assumptions for the force between the two bodies to be like point objects or something?
Yeah. Those things are there, and it will be again same. You can apply only for the particles or spherical bodies, because in case of spherical bodies, we can treat the mass at the center.
Okay, sir.
So, so these I can say Newton's law of gravitation is applicable for point-like masses or so Newton's law of gravitation is applicable for point-like masses, like mass or bodies with spherical symmetry. So for rest case, you have to do the integration if it is mathematically feasible, else you can't show. All right.
Yes, sir.
So generally, I mean, we are looking for accretion of those particles which are close to Earth's surface. That's what we call the G near the Earth's surface, right?
Yes, sir.
So let's say if you have a particle close to the Earth's surface, and if you release, what is the value of G at this point? So we can treat the distance of the particle from the Earth center as as good as the radius of Earth,
Yes, sir.
because the H is almost negligible. So you can imagine that the gap which I have shown is roughly 100 times the, maybe 1,000 times the Burj Khalifa. Yeah. So on a scale, if I assume this as Earth, the dot is almost 1,000 times the length of the Burj Khalifa. You can imagine how big is that.
Yes, sir.
So in general, in short, we reside almost touching the Earth, like we live here. Even the gap which we don't see is up to 1,000 meters, like maybe at least 100 meters. We don't, the gap we don't see. So when I say the G close to the Earth's surface, I'm saying that okay, if the particles are separated by RE radius, and G means the gravitational field, of course. So how much G will exist there? So G on the Earth's surface is
9.8 approximately.
no. The formula is
Or
G
GM by us, RE square.
RE square, and this we call G symbolically. So hence further our G will represent. So G by default we call it G capital M by R. That's simple. Okay.
Yes, sir.
So now generally we are interested in finding the G at any height from the Earth's surface. So we call it variation of G. Let's call it with height. So
So can you just come back in a minute?
yeah, sure.
Some.
Yeah. So if we have a, if we have to find the g at a height h from the Earth's surface, which is called altitude, the distance will change from a re to re plus h.
Yes,
So we have simple nice formula. You can just write the gm by re plus h whole square. That's it.
yes,
But sometimes this we can also write as gm upon re. We can take common and 1 plus h by r. And we know that gm by re is called the g on Earth's surface. So we want to relate things with g on surface. So the formula takes place in this form.
yes.
Okay. Just a minute. Okay. Now, in this case, okay, this is the formula in general, but we can make it more like approximate for the small value. So, if h is not very large, let's say you just climb the Burj Khalifa, which is not very large compared to the Earth, it's nothing, right? Although it's the biggest, tallest building on the Earth, but that doesn't make it really big enough compared to the Earth's dimension. So, having said this, we can use the binomial approximation, and we know this we can write as, and the power gets multiplied, right? I hope you remember. So in fact, you can see the g has decreased a bit, and if I try to find the decrement, the fractional change, so the gh minus g is how much? Minus 2h g by re. So the delta g by g is minus 2h by r. So you can imagine that the fractional change is very small, and in fact, you can find the percentage change in g because of this small climb. So you go to Mount Everest, and you know that this is the fractional change, and you can in fact find the value. So let's say Mount Everest is roughly 8,000 meters. Just a minute. So if you go to Mount Everest, H is roughly 8,000 meters. Let's say Mount Everest. We can make it simple. So 2 into 8,000 meters, and Earth radius is 64,000 kilometer, which is 1,000 meter into 100.
1,400 kilometers, right, sir?
6,400. Sorry, yeah. So 64 into 1,000. So this 1,000 cancel out. 1 0 is also cancelled out. 8 8 cancel. 2 4 cancel. And this is roughly 2.5%. I hope this calculation is okay. So you can see that on a roughly, even if you climb to the Mount Everest, the G will change by 2.5%. Now try to get the answer from the average value of G. So if I choose the Earth, if I take the sea level as G equals to 9.81. So what is the G at Mount Everest? So it is how much percent? 2.5%?
97.5 by 100.
Yeah. So you know that it is almost nothing, isn't it? The change is insignificant. You can just do this.
Yes, sir. Sir, just a second, sir. Can you just come back in a minute? My dad
Yeah,
is getting a call from one of his colleagues in my phone.
yeah, sure, sure. Oh, I think I have made a mistake. It should 0.25.
Sir?
Yeah.
Yes, sir.
So we made a calculation mistake. Actually, it is this much 0.25, and this turns out to be 9.78. So you can see it's very close to 8 is still, right? 9.8. If you go to Mount Everest, the G will change to value.
So it's like 0.025 difference.
Yeah. So anyway, so now we saw the G variation with height, and of course, any planet which is orbiting Earth far away will have different value of G. It's not the same G. The second is called variation of G with depth. So uh, again, we have to do the same. So if the radius is R, so from Earth's surface you go below. This means from surface how much you go below, right? So how far you are from the Earth's center? RE minus D, correct?
Yes.
So basically, you are actually sitting over this Earth, Earth of radius is small enough, right? There are many ways to interpret. So a point P is on the surface of a Earth of radius less than R, correct?
Yes.
We know that every layer beyond the point P, we can cut into thin shell. And we know that a shell cannot contribute to gravitational field inside, isn't it?
Yes.
The net gravitational field within the uniform spherical shell will be zero, if you remember from electrostatics definition.
Yes, sir.
So that is one way of thinking, and therefore you can just solve by writing the equation that okay, G at point P must equal to G m dash by R e minus. Why m dash? Because mass will change for the new Earth, right?
Yes.
Because the radius is small. The other way of thinking is Gauss law. That's the best. So gravitational flux, you can write as G dot dA, and at every point over here, the G will be towards the Earth center like this,
Yes, sir.
isn't it? So G dot dA is equals to minus 4 pi G into mass enclosed. And why minus 1? Because it's attraction, so it will have the flux will be negative actually. So the negative will cancel out. So you can write this as minus G into 4 pi R square. Understood? Why? G is the value, 4 pi R square is the area, and minus because it's inward, flux is inward, right?
Yes. So why minus 4 pi G? Oh, right. We derived it in electrostatics.
Yeah. So it is like if you compare the formula of gravitation, which is G m1 m2 by R square against 1 by 4 pi epsilon naught Q1 Q2 by R square Coulomb's law. The equivalence, you can see the G is equivalent of
1 by 4 pi epsilon.
so 4 pi G is equivalent of 1 by epsilon.
Yes, sir.
Okay. So using this relation, we can solve easily, no? Because we can write the answer in terms of density. That's better. And mass equals density into what? The volume, which is 4 by 3 pi R2. And therefore 4 pi cancels out, R square also cancels out somewhere here. Minus will also cancel. So G is how much then? Four by three rho pi G R, like this. And why this is important to see this formula this way, because density of planets are something which we can compare. So mass and radius can change, but density is something which can give you the right answer. So first of all, it depends on the density. It depends on the size of the planet. So G depends on the two things. For a given density, what is the size of the planet? Let's say what is the value of R? And if you want to write in terms of like this is GD, so that's at depth D. So it's pretty easy now. Four by three pi rho G R. Okay. So G on the Earth surface is how much? What is G value? 4 by pi 3 rho G capital R. That's it, isn't it?
Yes, sir.
So the relation is pretty simple. The GD by G is R by R. So GD is how much? Simple. At any depth, but we are okay. We are looking the answer in terms of depth, not the radius, right? What is R? RE minus. The formula is simple. 1 minus. Simple formula, right?
Yes, sir.
Which means if you go D below the density, the G will change by this formula, and if you go at the center, G will be 0, and that's logical because mass enclosed is 0.
Yes.
So at center, the G is 0. So as you go away from center, G will increase, and it will pull you towards the center because the direction is towards the center, right? Now, what is most interesting is that G is function of R, so it is a good question of SHM. So if I draw the Earth, and if you make a hole, sorry, if you make a hole along a diameter, this is the hole you're making. So at center, if you have a ball, it cannot move because there is no G. The moment you slide, the moment you shift by any value, let's say X, then G at this point we know. So from center, if you go distance X away, the value of the restoring force will be how much? Mass of the object into G. Just a minute.
Yes. Sir. Sir, are you able to hear me?
Yes. So the restoring force is M into G, and but the G of that location is how much?
M into minus GX by RE.
Yeah, so it's Gx by R, correct?
Yes. Sir.
So you can see clearly the acceleration of the particle will be minus F restoring upon mass. Why minus 1? Because we're writing vector equation. This is a vector equation.
Yes. Sir.
So this turns out to be simple G by RE into X, and we know the relationship is minus omega square X, the standard equation of Einstein.
Yes. Sir.
So if you compare the relation, what you can see that omega square is how much?
3 by RE.
So times it will be 2 pi under root RE by G.
Yes. Sir.
But this is not sufficient. I mean, we need to understand something more. And this G is the G on the Earth's surface. And if you remember, the value of G on the Earth's surface is how much? 4 by 3 pi rho GR. Which means, I mean, of course, I'm the mess. 2 pi. It is 3 upon 4 pi G rho G. Understood? Or you can take a 2 pi inside, you will get as 4 pi square, which is 3 pi by. Such a nice formula, right? Look at the formula. I mean, it gives a lot of information. I'll discuss something more practical use cases like how it can help Elon Musk in designing the transit system, which can take you from one place of the Earth to the other place in a fixed time, no matter where you want to go. Now, this is interesting. The time period is constant, right? Also, while solving this question, we never use the approximation, which means the answer is true for any displacement. So no matter what's the amplitude, the time will be same. Now, what does it mean? We need to discuss a bit more about it.
Becomes faster. I mean, like it first moves really fast when we displace it by a
Yeah.
higher amplitude.
Yeah. So if you draw infinite tunnels from beginning from the surface to the other point, if you simply draw infinite tunnels, okay, of course we won't be able to make tunnels through the core of Earth, but at least we can join the small tunnels, like and the small tunnels on the Earth is big enough for the cities, right?
Yes.
So even though if I able to make a tunnel, I'll just show you just a bit. So this I'm seeing that on a practical scale, I can make a tunnel like this. That's it. And this will be big enough. I mean, this is like joining two cities at least maybe few thousands kilometer away. Few thousands, not 1 2 kilometer. They're like few thousand, maybe. Imagine like to move 2,000 kilometer on Earth surface. How much angle we tilt theta? So we can set theta into r equals to L. L is theta into r. So theta is how much? L by r. L is roughly 2,000 kilometer and r is 6,400 kilometer. So this turns out to how much? This is 0 gone and 4 5 and 4 16, and this is roughly how much radian? So 5 by 16 radian into 180 degree. No, sorry. This is 5 by 16.1315. So this divided by 3.14 into 180. It is roughly 18 degree, 18 degree. If you turn, and I think 18 degree is not much, right?
Yes, sir.
Oh, so my approximation was correct. If you can imagine that this is roughly like 18 degree, not this is even more actually. So 18 degree will be something like this one. That's it. This is something like 2,000 kilometers. Imagine you need to draw a tunnel very close to the surface. That's interesting calculation. And therefore, the time period is fixed 3 pi by rho g. Density of every planet is constant. On an average, we assume constant, not constant. As such, but we can assume the density of the Earth. So that is mass upon volume, and the Earth's mass is roughly 5.96 per 24 kilogram, and radius is 6.4 into 10 power 6 meter cube. So density turns out to be 5.96 into 3 upon 4 pi into 6.4 whole cube. Oh my god. Into 10 power 6, right? Kg per meter cube. Also, we are not a very dense planet. Okay, planet wise, we are just okay, not much dense, which is good. You can play on the ground, no? Yeah. So nothing bad. Oh, so roughly the density of Earth is 5427.7. Uh, this is average value, of course, which is like 5.5 times the 5.5 times the density of water, right? Yeah. So we are 5 times denser than water on an average, of course. And if you try to find the time period, let's say I'm just interested in the actual value of the time period. So this is okay. I can search the density of Earth on Google, and I hope we should get the same answer. Density of Earth. Ah, that's very close. It's 5.51. Very excellent. Okay, they take 5.51 gram per centimeter cube. So it's okay. All right. Nice. So when you do calculation, you feel nice, isn't it? So 3.14 upon we got a density of as 551. Let's get equal to 0 into 10 power G is 6.67 10 power minus. And you, of course, don't worry, the answer will be in seconds. So I love calculation in gravitational. I'll show you all the real calculation, like how things are happening, and yeah, yeah. Then hmm. So it is roughly 5, okay. Divided by 3600. Yeah, it's very famous answer. You know how much is the answer? This is roughly 1.4 hours. I was knowing this answer, but just I wanted to calculate again. No matter which tunnel you dig, you can reach the other end in half of the time, 70 minutes. Because this is a time period, no? Time period is like twice. You go back and forth. This is when I say time period, you will go from here to here and will come back, right? But to just go, this is the round trip journey. So possibly we can make the fastest mode of communication without using any force or anything. Just let the gravity do the job. And what is interesting is that once you release without friction, the other end it will reach automatically, and we also will come to rest. So what the only thing you need to do is when it will come to rest, you just hold it there. Okay, simple. So in 70 minutes, you can go from anywhere to anywhere on the earth. Technically, it's possible. So imagine one fine day we are able to dig a hole across the earth. Then imagine how the world will be. Like no matter whether you live in America, you live in India, you live in any damn part of the world, the time taken to go is just 70 minutes, right?
Yes, sir.
In a traffic condition of Mumbai, that is like going just maybe 10 kilometers away. Okay. Anyway, that's hypothetical world. When we are not going to dig such a big tunnel, that's next to impossible.
Sir, I don't
Okay.
understand like why any tunnel that we dig, it will have this time period, sir.
Okay, okay, that's good. So yeah. So what we'll do is we can choose some random tunnel. Okay, we have derived for the one tunnel, no? That's passing to center.
Yes, sir.
So what if we have a tunnel which is not passing to center? So let's say you want to go from here to here. Okay, I'm drawing it horizontal because that's easy for me. But it doesn't matter, isn't it? For Earth,
Yes.
everything is same. So again, it's the same philosophy. Same. If you are here, you will be at rest because gravity will act this way and you cannot move this way, correct?
Yes, sir.
If I displace by x now, the gravitational force will act this way, right? Let's call it r. So from center it is r. Let's call it theta. What is the restoring force?
It's F cos
F
theta.
cos theta. which is mg cos theta. Isn't it? And what is G, by the way? Same answer.
Yes, sir.
G is always like G at that location. G is in general, so formula is G on the surface into R by capital R, if you remember the answer.
Yes.
But what you can see again interesting that the RE cos the R cos theta itself is x1. So no matter which you choose, the omega square will be same, right?
Yes, sir.
So does it change if you go to other tunnel? It's the same answer, right?
Yes, sir.
So that is the reason every tunnel will exhibit the similar SHM, and so the time period will be constant, and that is why if you dug a tunnel or if you simply think hypothetically, the time taken to go from one end to other end is constant, and in fact that is answer we know is 3 pi by rho g under rho. Okay, so this is a very famous answer, 3 pi by rho g, which is roughly 114 hours. Just for I mean curiosity, we got this answer, but you can remember the formula. No, don't remember. In fact, you should know how to derive it because that won't be difficult, right?
Yes.
Oh. So we can do really nice problem like using time period concept. So we saw that the tunnel problem, and we also saw that the gravitational field as you go within the Earth will decrease, and that is logical because as you go inside, you actually stand on a planet of lesser mass, isn't it?
Yes, sir.
So coming at the center means you are not standing on any planet. You are just empty, and that's why there is no gravity, there is no force, nothing is there.
Yes,
Now,
sir.
if you talk about the hollow shell, hollow spherical shell, the same thing. Like if it is a shell, the G cannot exist inside, right? So G inside is how much? Mass is empty. So G will have only surface and beyond. So G in general will be equals to G m by R square, where R should be more than equals to surface. Okay? Because inside we cannot have G, isn't it?
Yes, sir.
Do you realize this? What I'm saying? So you can again apply the Gauss law. No? Then, like you see, there is no mass enclosed, and so the answer, right?
Yes, sir.
And for point outside, it is like a point mass of value capital M and kept at the center. So by knowing the distance, you can find the answer, isn't it? Then you can do the all the things like if the density of the Earth is varying, uh, and then find the G as a function of R. Those things inside and outside, and you can do variety of calculation, isn't it?
Yes, sir.
Now I'm not going to repeat this because we have done enough in electrostatics, and the moment you encounter in gravitation, I hope you can do on your own. Okay. All right. So now we can go to some hypothetical scenario. So imagine what if we have one fine day you get a very long cylindrical planet. So the planet is cylindrical. Anyway, control the so this is the plant as you can see. All right. And now around this plant, so maybe a satellite is orbiting that we can do question later on. So if the distance is our density is rho and it's infinite in length, so what is the gravitational force on the satellite? So let me look at satellite.
Using Gauss theorem, we can solve it.
Yeah, exactly. You have to think of Gauss theorem only, and you can take the radius of this cylindrical planet as r. R. So this is like a hypothetical planet, and you can solve this question. That's easy. So okay, find the force on satellite.
So,
Yeah.
sir,
Got the
I'm
answer?
getting yes.
Yes, tell me.
Hello.
Tell me,
Sir,
tell me.
I'm getting m into 2 2 rho pi r square g by r, sir.
2 rho pi r square G, sorry, capital G by small r, like this.
Uh, so r I'm getting so r only, sir. Small r.
Yeah, yeah, that seems to be correct. Right? It's 1 by r only. So the answer, if you remember, the answer is very simple. It's lambda by 2 pi epsilon not r. If you remember the electrostatics, right?
Yes, sir.
So I'll show you the conversion. Like you can just write like this: lambda will be density into cross-sectional area, and 2 pi r is okay, and the 1 by epsilon is 4 pi g. That's simple.
Yes, sir.
So you see the same answer which you got: 2 rho pi g r square m by r. I think this is your answer also. Yeah, that's correct.
Yes, sir.
Now, if satellite is moving in a circular path, because then only it can be stationary. So, for what orbital velocity it is possible? So, what is the orbital? This is called the orbital velocity. In fact, we come to know this. So, the orbital velocity of satellite must be
So p square by r is equal to the g value, sir.
correct. Now, you will see something really interesting that we have done this in circular motion, if you remember. But the formula is 2 rho pi capital G r square m by r, and this is also m v square by r, correct?
Yes.
And what you can see that the value of v has nothing to do with the mass. It means to move around the planet in a given radius, you must have this velocity. So whoever wants to come to that radius, the only criteria is the velocity. The mass doesn't matter, isn't it? You can see the velocity is entirely a feature of. Oh my God, that's interesting. This is a constant value to turn around any orbit, isn't it?
Yes, sir.
This is fantastic answer. The thing is that for infinite cylinder, no matter how far you go, you're supposed to move with only one value. The reason is as you go away, the cylindrical length which you can observe will become more and more. So essentially, the relative separation will never grow, and that's something difficult for you to as of now realize what I'm saying. I'm saying that the visual perception of the size. Let's say if you see something in front of you, can you see all infinity at once? The answer is no. You see a small part. So you can take a ruler in front of your eyes. How much you can see if it is really close? A small piece.
Yes, sir.
So don't turn your eyeballs left right. Just look at front. So can you see the entire scale if it is very long?
No, sir.
Now you take it away slightly. Can you see more?
Yes, sir.
Take it slightly away. Can you see more even than that? Yeah, the answer is yes. You can see more and more. And what I'm saying is that as you go away from this cylindrical plant, which is infinitely long, the force will vary in such a proportion that the centripetal force uh, and okay, so the whole idea is like as you go away, the velocity requirement to move around the planet remains same. Like you just need to move with same velocity around the planet at any distance. Like the distance really doesn't matter.
Call from +91.
Okay, all right. So this is nice answer, and you can also see that the kinetic energy is again constant one. So what is the kinetic energy of satellite? Half m v square So you can do variety of calculation like this, and that's why I have shared the entire gravitational sheet with you. And this sheet is a detailed course of gravitation which I took in those batches where I haven't taken the electrostatic first. So when I teach electrostatics later on, and if I teach gravitation before, then I do the same thing with gravitation. So that in electrostatics I cannot teach. I mean, I don't need not to teach everything. So you can see all types of problems that we have solved before. You will see here, and that's why I'm leaving up to you to read and understand. I will not do much about it. Okay. So I will discuss only few things which is not part of the discussion as per se gravitation. Okay.
Yes.
So okay. So we'll talk about something like cosmic velocities. I will not talk about potential energy, potential. All these things are done there. It's a very detailed notebook, as you can see. It's yeah. So now we can do the okay. First cosmic velocity. So the first cosmic velocity is also called orbital velocity, and our derivation will be in context of spherical planet. So we are going to draw the spherical planet in any case. If you don't like some color, you can let me know. I'll just change the color. Okay, I think you like this. I don't like it. Bad. Huh? This is okay. Too bright. You want a lighter one, like a matte finish.
This is itself all right.
This is fine. Now we draw an orbit around the given planet. So our planet is Earth mostly. So we'll study in context of Earth, but of course you can generalize this formula for any other planet. It's only formula. So the distance is r and the altitude is h, radius is re. And you need to be careful about the terminology used in this chapter, like altitude and distance. So distance means from center to center, and altitude means from surface to the object. Okay. Basically, altitude means height. Okay, we know this.
Okay.
Sorry. So to derive the orbital velocity, it means orbital means the object is moving around the planet. Satellite is in orbit, moving in the planet in a circular path.
So why is the name first cosmic velocity?
Okay, we come to this. Let me. So the satellite is moving in this orbit, and the distances are. So the force which is responsible for the motion of satellite is gravitational attraction, right?
Yes.
So gravitational attraction will give you the required centripetal force to let you move in a circle, isn't it?
Yes.
And that is why we call it orbital velocity. So the gravitation is pretty easy to write G m Earth m satellite upon r square, and this is equals to mv square by r, correct?
Yes.
And again, what we need to understand that the mass of satellite really doesn't matter. But now you can see that for a spherical body, the velocity is inversely proportional to square root of r, which means as you go away from the planet, the motion is really easy. With a small value of v, you can turn around the planet because a big radius means the change is small, right? Isn't it?
Yes.
So as the radius turns to infinity, the speed needed to turn around the planet is really, really small. You can just have a very small value, can still turn. Okay, so you can say that infinity means the orbital velocity is almost tending to zero. It is like stationary, nothing is in motion. Even though motion is there, we can't see. Nevertheless, so we call it orbital velocity. Generally, we calculate near the Earth's surface. So near the Earth's surface. Okay, when I say near, it may be up to few hundred kilometers. So maybe 200, 300, and 400. So very close, it is going to be the smallest radius, and so the V naught will be how much? Gm by Re, correct?
Yes, sir.
So near the Earth, R will be equal to R, isn't it?
Yes, sir.
And we know that this we can write as Gm by Re square into Re.
Yes, sir.
So what is Gm by R square? This is called small g, the Earth gravity on like the acceleration due to gravity near the Earth's surface, right? GRE.
Yes, sir.
And this value turns out to be roughly 8 kilometer per hour per. So you can imagine if you want to orbit Earth, so those satellites which give you the weather forecast, they are close to the stratosphere, so they are not very far. So because they live in the stratosphere, so what they do is they orbit at a very high speed, 8 kilometers per second. Can you imagine how fast is that?
Yes, sir.
So in a blink of the eye, it goes 8 kilometers on its orbit, but the orbit is of course 2 pi r. So even you can find the time period. How much time to take, by the way? So time period will be how much? How much? And guess.
6,400 by 8.
So time period will be. We can have a better formula. The formula you can write is okay. Okay, there is a direct formula, but anyway, you can write as 2 pi r e upon v o, right?
Yes, sir.
2 pi r e upon g r e. So I think this will be 2 pi under root. Yeah, r e by g. That's fine. Yes. And RE by G you can solve roughly easily. It's easy to solve because RE is 60, just a minute, 6.4 into 10 power 6 meter, and G you can take roughly as 10, correct?
Yes, sir.
So roughly it is 2 pi and 10 power 5 and 10, 64 into 8 into 10 power 2. I think 2, no? Sorry, 4, 5, and 2. Yeah, 2. So yeah, we are finding time period. This is these many 1600 pi seconds. Not much. So how much time it will take to complete the entire circle around the Earth?
5 seconds.
Again, the beauty. The answer is again 1.4 hours because it's the same formula.
Yes, sir.
This is like magic, no? Like no matter whether you solve inside this 3 pi by rg, before that you had the formula. Same answer.
Yes, sir.
So whether you move around the planet or you move inside the planet, there is no difference of answer. It is always 1.4 hours, isn't it?
Yes, sir.
Okay. So now you know that to take the weather forecast of the entire world, the satellite will just need 1.4 hours. That's it.
Yes, sir.
That's interesting. Okay, anyway, coming to
If we are able to do this, I mean, like, if this logic applies to even above the Earth's surface, then what about like the flight time, sir? Why is it
the
not less?
flight time is time of you're saying time of flight.
Say the flight time means like airplanes, sort of.
Okay. Okay. Yeah. So the problem is like the planes. Here the assumption is like there is problem which we don't consider. The satellite will turn, but Earth is also moving. So the location of Earth is also changing very rapidly, actually, and therefore, I mean, first of all, we cannot launch the plane at that speed. We cannot attain that speed at all, which is 8 kilometers per second. So V naught is something that we need to give actually. I mean, a satellite which is in this orbit will have this much velocity. So any velocity less than this will not let you in that orbit. You have to go away from it. Okay. And the height, even though we are talking about the height, these heights are much more than the Earth's atmosphere, much farther away. Planes fly in the close to the Earth's surface. Its plane height is not much. It's like 2 to 6 kilometers only. That's it. Maximum 8 or 10 kilometers. And you can find the clouds almost near about 2 kilometers. That's why you see the cloud below it, but not much below. I mean, you may see 1 kilometer below. Okay. So
Yes,
typical
sir.
height of the plane is, and the problem is, plane cannot fly at very high altitude because the whole idea of aerodynamics depends on the air density. So going up will require a very high speed to propel because we don't have much air left.
Yes, sir.
So there are two problems. Helicopters cannot fly at high speed, high altitude. That's the first problem. Even the plane cannot fly at high speed.
The call from +912241616728.
And that is why, like during the Kargil War in 1998, when you were not born, the major problem was why we won the war because we had supersonic planes, and the Kargil War happened at a very high altitude, like Siachen and Glacier. Now they are so high; it is roughly like you can imagine close to the Mount Everest height. Okay, that way you can think of it. So at that height, we cannot, communicate using helicopters. So we cannot take the weapons and various arsenal to the height. But India had the, I mean, fighter planes, which is much advanced. And fighter planes can actually fly at very, very high altitude because they move at such a high speed that aerodynamics to sustain their flight can be achieved in the least possible density of air. So we were able to communicate from the base to the war area using fighter planes. The normal plane cannot sustain because of the issue is aerodynamics. Okay. So the planes can fly because they have long wings. So they produce enough airlift to sustain. So those planes which goes a long distance, they have very large wing span. You can see their wings are really large. And the shorter planes having the small wings. So all depends on like the shorter planes will try to fly at low altitude, and the planes which are like having big wingspan, they fly at a big altitude. You can in fact see from plane that there are many planes flying below your plane, isn't it? You can see that. That's
Yes, sir.
really small.
Yeah,
Anyway,
that's
this
why
I
even satellites have a very large wingspan.
yeah no no but no 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 that's a different satellite wingspan is the satellite place is having no atmosphere or at all. It's like zero atmosphere almost
Oh,
because we do not afford we cannot afford resistance. The satellite wingspan which we demonstrate is basically the solar panels for the energy absorbed. So they are generating the energy using the light actually, because we cannot send batteries and all. No?
Yes, sir.
So the power, the way we create the power backup is the solar cosmic radiation. So the solar light which comes near the Earth, the wingspan of the satellite is essentially solar panels. And you know how big the panels are? Can you imagine how big the panels are?
Sir, I don't know, sir. Maybe a few 100 meters.
It is up to 2 kilometers.
Wow.
Yeah. So the unfolding is super phenomenal. Like it is the perfect origami which we wrap in a small way, and then they unfold to span up to a few kilometers. I mean, yeah, because they need a tremendous amount of energy to do the navigation, do the like computation, browsing, upload, downloads. You can imagine the amount of work going on there, right? So
Yes, sir.
imagine the amount of picture you capture, the video images, and you have to send back to the earth. So we have the uplink, we have the downlink. So there are variety of event taking place which requires tremendous energy, isn't it? So computationally, the energy requirement, uh, how you can send the current there? We don't have the electric connections, right?
Yes,
So
sir.
the wingspan basically represents solar panel. So I'll just check how is the span. That's a good question because I may be wrong, but I know the International Space Station is. But
Your voice is cracking, sir. Hello, sir. Sir, I'm not able to hear you.
hello, hello, hello. Am I audible now?
Yes, sir.
Okay, okay. Yeah, so it's big enough. I mean, it depends. Like the solar panel of ISS, the wingspan. This is really huge. The ISS. Yes, NASA is using uh, solar arrays. Each of 8 solar arrays is 112 feet long by 39 feet wide, and this is how it is spanned across. Okay. And they generate electricity roughly which can light up 80 homes in America. And the total a solar array wingspan is 65 meters, 73 meters. Okay, and then there are such 8 values. So maybe you can say half a kilometer. Yeah, more than half a kilometer. Yeah. So good information from the NASA. Am I audible?
Yes, sir.
Okay, so this is the first cosmic velocity, and to get the cosmic velocity, what we need is just the circular motion concept, and what is the further interesting that the time period is again going to be same answer, 3 pi by rho g or yeah 1.4 hours. This is a rough value, 8 meters per second, but you should remember this.
Okay, sir.
The next concept is called second cosmic velocity. And the second cosmic velocity is the name that we know actually is called escape velocity. Escape divided by VE. And what is escape? Escape means you want to escape the Earth's gravitational field. Okay. So we'll try to understand the meaning of escape. So let's say this is sun. This is sun. So if I take Earth as the satellite, because that we can assume. So for sun, Earth is like a satellite, isn't it?
Yes, sir.
For Earth, the moon is like satellite.
Yes, sir.
And there is really interesting happening. I mean, the moon is orbiting Earth. And this entire thing is orbiting sun in some circular path. So there is a concept of let's say Earth. Hmm. So if you look at the entire solar system, it's really interesting that things are happening in a very localized fashion, which means the moon is not much affected by sun's gravity because it's really far. I'm not saying it is not affected at all, but the local gravity of Earth is predominating feature compared to the sun's gravity, which is very small. Understood? The distance between the sun and the Earth is called one astronomical unit, AU, astronomical unit, and one AU is roughly 1.5 10 power 11 meters. And how to determine this answer? So roughly the time taken by the light ray to reach Earth is, you know how much? How much time light takes to reach Earth? It is 500 seconds.
Yes, sir.
So distance you can write as VT, or you can say CT, the speed of light into time. And light speed is 3 into 10 power. How much? 5. 3 lakhs kilometers. So this is 3 by, yeah, what I'm saying this. So 3 into 10 by 8 meter per second, we know the answer into 500, which is how much? 1.5. That's simple, right?
Yes.
Now, what is happening? Like, there is a concept of a ruling planet, or in Hindi we call it Swami. The Swami means the ruler of things, the governor actually. Swami also means in like the owner actually. So there are many ways in astrology. Basically, in astrology, we use the word Swami. Like Swami, the who rules your planet. So even a zodiac sign, we have the concept of Swami and all. So the moon is governed by Earth. So Earth is the Swami of moon. Okay. So the localized motion is controlled by the Earth. Otherwise, the other motion is controlled by the sun only. The next ruler is sun, which is the ruler of Earth itself, the Swami of Earth. And in planetary motion, we only respect the Swami. So when Swami is gone, then the Swami of Swami becomes your Swami. Now that's interesting. I'll come to that. So I'm talking about the condition that why something will leave the earth. Imagine from earth you throw a particle, you throw something, and the question is how fast we must throw so that it should never return to earth. The minimum velocity with which we must throw object which will never return back to earth is called, and return back means it becomes free from the gravitational interaction. So they stop interacting. So the definition is it is the minimum velocity required to leave the Earth's gravitational field. Now, technically, field is spanned up to infinity, so you cannot leave the field theoretically, right? So here, when I say leave the Earth's gravitational field, it means the dominating field should not be Earth. You must change the Swami. Now, who will be the next Swami of the object? So if you throw the object with escape velocity, it must land to the same orbit as that of the Earth. And the Swami will change from Earth to Sun. Understand?
Yes, sir.
So you may throw with escape, but after landing, so everything which we throw with escape velocity actually leaves the planet and goes to the next Swami called the Sun. And this Swami will govern your further motion into the orbit which is same as the Earth. In a way, the object itself becomes a new planet, because anything which is governed by sun is called planet, isn't it? Of course, there are some other uh, constraint or the definition that when we say planet, when we don't say planet, I mean those things are defined by NASA and the astronomers of the world. I don't know much about it, but what I can say is that the velocity with which now you will move is the orbital velocity of Earth with respect to sun. So what is VOES? Orbital velocity of Earth with respect to sun. So just like moon is orbiting Earth, Earth is also orbiting sun, and Earth is moving in the orbit around the sun at a distance called 1 astronomical unit, isn't it?
Yes, sir.
And because Earth is also moving with same velocity, VOES, and therefore in the frame of Earth, what will be your velocity? Zero. Because in the frame of Earth, you will be static,
Yes, sir.
a non-moving entity. So to solve the question of escape velocity, we have to use the energy conservation. We cannot solve by the force and all method. So we have to use the energy conservation. So using conservation of mechanical energy, the case initial plus U initial. Plus simple. K initial, okay, we are writing the Earth frame only. Half m v escape square, correct?
Yes,
So what is the initial potential? Minus gm. Now, if you remember the electrostatics is k q by r. So here we have gmm by re minus because it's an attractive potential which is negative. But eventually you come to rest as we have discussed. So k final is going to be 0. And because you are at infinity, there is no interaction. So potential is also 0. So everything is 0. Understood?
yes,
And therefore, or in a way you can think that you give some positive energy to overcome the negative potential energy. So you just overcome this barrier. You can see the V escape turns out to be 2GME upon RE, which you can write as 2GRE under root, right? If you remember the GMR, you can write as GR, correct?
yes,
By multiplying with RE numerator. And therefore, this is like a root 2 times V orbital,
yes,
isn't it? It is root 2 times V orbital.
yes,
And we know this is roughly 8 root 2 kilometer per second, which turns out to be 11.2 kilometer per second. If you can really throw this fast from Earth's surface, it will leave you, will never come back.
yes,
So why this is required? So of course, if we are trying to go to the different planet, let's say if you want to go to Mars, so we have to have enough fuel to overcome the Earth's gravity, and somehow we have to enter the Mars gravity because the rest Mars will do. Understood? So Mars will take care of everything. Like you go to their field, and the Mars will pull you towards itself. And with some maneuvering, you can reach there. Not a big deal. So we'll come to that how to land on a planet. It's very interesting concept of mechanics, and it involves a lot of calculation that how to reach the Mars in the least time, what is the least distance. Because when you launch something, the Earth is in motion, right? But
yes,
also Mars will be also in motion, no?
yes,
So it is like you have to jump from one football to the other football in which football is moving. So to make the shortest jump, you must jump such that while landing, the other football should be below your foot, isn't it?
yes,
That's like you can understand what I'm saying. This is it is like this. I mean, what I'm saying is something. So we have, let's say, two orbits around the sun. Imagine, I mean, I'll take a simple case. So, and sun is in the center. Let's say sun is at the center, just for a simple example. And this is Earth. The the blue-eyed boy is Earth, maybe mother. Okay. And Mars is the really dirt. So maybe Mars is here. Let's say. But what will happen if you try to jump? Will it be there? So while if you launch this way, then when it will reach here, the Mars will be here, isn't it? That's the problem.
yes, sir.
So we have to minimize the effort of landing on Mars. So we wait for the right time. So let's say we try to reach the Mars on the least possible time. How to make it possible? Uh, so you are smart enough. So the two planets are the nearest distance of the two planets is this much only. So we always launch for the nearest distance. So you will launch for this point. And while you're going there, the Mars will be coming towards you. And the moment you reach here, the Mars will be exactly there. I can see the consumption of fuel is least. We have traveled the least distance in the space, outer space. isn't it?
Yes, sir.
Yeah. So we jump by calculating the time taken for me to reach the other orbit, and I'll make sure that while the time I reach the orbit, the Mars reaches that location of the orbit, so that I can make the landing effectively and easily. So is it going to be easy task? No, it's very difficult task. So imagine that the kind of calculation and the precision you need to land at the right time at the right place. Else you will miss the planet. Imagine you reach there, there is no planet. So you will go to some other place. That's
Yes,
dangerous,
sir.
right? So we have lost many satellites. Let's say we have lost Voyager, and now Voyager has gone much beyond the solar system. So we have two satellites, Voyager 1 and Voyager 2. Voyager. And they have left the solar system long time back.
Do we have connection to that?
Yeah, we do have connection because they keep on sending signals which reach Earth after, I mean, every few years we receive something. So till now, I think the Voyager 2 is connection. Voyager 1 has lost connection, I think, and it has gone to some other universe. I mean, that's interesting. Oh, that's so cool. Just
The call from India plus 919121622121.
all right. So okay, this is all about landing and launching of satellites. That's a big deal. Now we have solved the most classic example of escaping from Earth's surface, but when we create numericals or questions, I may think of launching a satellite not from the surface, but what if I want to launch satellite from somewhere inside the Earth? So let me make a hole, and I call this as center. So let's say you are the Russians who are very like doing some secret launching, and they're not creating their satellite on the Earth's surface because the satellite orbiting Earth can watch and capture the images, and America will come to know. So because there is always a war between the America and the Russians. Russians are like villain, and Americans like the savior of the world. That's how they project their movies, isn't it?
Yes, sir.
Okay, it's not the case. I mean, even America is as bad as Russia. None of them are good. Okay, so you are making satellites here, and you're trying to launch from inside the Earth. Maybe I can say RE by 2 distance. The only thing that will change is we're trying to throw to escape the Earth, and therefore the escape velocity. How to calculate? The answer is simple. Just write the energy consumption because eventually you have to escape the Earth, which means the final kinetic and final potential must be zero. So the initial kinetic you can write as half mv escape square, but the potential will be m into potential at point p, like just like the q into vp potential equals to potential, like this. And why I'm writing this? Because the potential inside the solid sphere was the difficult formula. If you remember, it was like kq by 3r cube, 3r cube, yeah. Oh, sorry, 2r. into 3r square minus r square. Do you remember this formula? So in electrostatics, we had this formula. Okay, hopefully you can revise and you can get to know this.
We're doing this.
Yeah.
But I don't remember the formulas.
Yeah. So now, if I want to convert this into gravitational formula, the only point is, first of all, make it negative, because everything becomes positive, becomes negative, because the gravitational force is negative, so the answer will be negative answer. And second is k becomes g, q becomes m. This is not a big deal. I mean, 3 re square minus the distance from center. That's it. So here the r given is re by 2, correct? Because the launching site is re by 2 away. So the potential at point P is how much? Minus. So it turns out to be 12 minus 1, 11 minus 11. So minus 11 GM by 2 R 8 R, right? I think this is the right answer.
Yes.
And therefore, now we are good to write here half m v square minus m, because it's minus. And now you can see that v square becomes 11 GM by 4 R e, which is like 11 by 4 GR. And definitely it is more than the previous value, because this is like more than 2, right? It's roughly 3 GRE, isn't it?
Yes.
Okay, so I will leave this question is now I have shared the notes. What I will suggest that you have to go through the entire notes, and I will discuss the next class. I will discuss the something like Kepler's law in detail, and a few questions of energy and angular momentum conservation, and the rest I will expect you to study from the notes. Okay. So make a revision of it. It will revise your electrostatics part also, and make a list of the important formula which you find difficult and is actually important also. So do those things, and gravitation we can finish in next lecture. But before next lecture, you have to finish the notes, reading entire. Okay.
Okay, sir. Sir, so tomorrow we are not having class, huh?
Tomorrow is what, Saturday? No,
Yes.
tomorrow I won't have any class. Yeah. All right.
Yes, sir.
Okay.
Thank you,
Bye. Take
sir.
care.
Bye, sir.